Okay, so as I was saying, when I was first asked to do this, I was asked to talk about what mathematicians do, and I thought about this for a long time and determined that this really was not wouldn't be very informative to the average person who's going to be seeing it. So I thought about my career as a mathematician and how I developed and changed. And I want to tell you about how I developed and changed and what I learned. And I want to do it using a single theme as I go from myself as an elementary school student to myself as a faculty member today. And I think I found a theme which everybody here will be able to see and understand. When I was very young, I went out to a bookstore, which these still existed at that time, and I obtained this rather remarkable book, Mathematics and Logic, Retrospect and Prospect, by Mark Katz and Stanislaw Ulam. And looking back on it from the experience of over 50 years, more like 60 years, I find it a great wonder because I wonder if I understood anything of this book at all when I first obtained it. Certainly it was new, certainly it was different, certainly it was a door into something that I didn't understand. Very interesting, the book talks about a science and an art. Mathematics is a science and an art. And this quote, in one sense, mathematics is an autonomous intellectual activity, devoted as much to beauty of technique as to results. In another, it's perhaps man's most valuable tool for understanding the physical world. And this is paradox. And I really found this book to be the launching point. I still have the book after 60 years, and it's really a launching point in me trying to understand mathematics. And there are many things in this book, many things which I understood and didn't understand at the time. But one of the fundamental things in the book, and one of the hardest things I've discovered in mathematics, is the question, how do we count? Now, at some level, this question seems too silly. I mean, of course, we count with the natural numbers, 1, 2, 3, 4, 5, right? And if you go after this talk and you talk to your parents and your parents say, what great mathematics did you see in this talk? And you say, well, I learned, the guy was talking about how to count. More likely than not, the response is going to be, doesn't everybody know that? And I think the answer to that is no. Not everybody knows how to do that. And what I hope I'm going to do today is tell you a little bit about how to count. So now we come to the first part of the talk, and I'll call this part elementary school. So when I was in elementary school, I bought, probably about the same age that most of you are, I bought this book, Mathematics and Logic. And one of the things that's contained in it is the idea of a binomial coefficient. And a binomial coefficient is an expression for two positive integers, n and k. It's given by this symbol. And it's the number n factorial over k factorial times n minus k factorial. Already this is an interesting number in how we present it. N factorial is just the product 1 times 2 times 3 times 4 times n minus 1 times n. And this is a number that grows very rapidly with values of n. So n like list n over n factorial. If n is 1, well, it's 1. If n is 2, n factorial is 2. If n is 3, n factorial 6. 4 is 24. 5 is 60. 6 is 360. And then it grows very fast, and it grows very much faster thereafter. So n factorial is an interesting number. It's n factorial is the number of ways to linearly order n objects. So if we have 3 objects, 1, 2, and 3, I can order it as 1, 2, 3. I can order it as 1, 3, 2. I can order it as 2, 1, 3. And 2, 3, 1. And I can order it as 3, 1, 2, and 3, 2, 1. And as you can see, there are 6 ways to order 3 things. 24 ways to order 4 things, 60 ways to order 5 things, 360.
In the checkbox, someone wrote 5 factorial is 120.
Oh, hold on. Oh, I'm sorry. I divided by 2. And that makes this is 720. So n factorial is the number of ways to linearly order n objects. So already this number is very interesting. We're going to take n objects, and we're going to look at the ways of linearly ordering them. Then we're going to look at dividing by k factorial and n minus k factorial. And this, remarkably enough, is always a natural number if n and k are natural numbers. And that's for a very simple reason. N choose k, which is n factorial over k factorial n minus k factorial is the number of ways or the number of subsets with k elements of an n element set. And now I'm just going to assume here that k is less than or equal to n. So it's a number of subsets with k elements of an n element set. So how can we look at that? Well, if I have an n element set, there are n ways to pick the first element of my subset, n minus 1 ways to pick the second element of my subset, and then the kth one, n minus k plus 1 ways to pick the kth element of an n element set. And then there are k factorial ways to order those elements. So if I picked x and y, and I picked x first and then y, it's the same as picking y first and then x. So I can divide by the number of ordered ways to pick them. And that tells me, since this is just another expression for n factorial over k factorial n minus k factorial, I just dropped off the last n minus k through n minus n, or 1 elements of the numerator here. This binomial coefficient, n choose k, is the number of ways to choose k elements from an n element set. And since it's the number of ways to choose this, this always is a natural number if n is bigger than or equal to k, is bigger than or equal to 0. Of course, n choose 0, there's exactly one way to pick a subset with 0 elements. So that always is 1. And n choose 1 is always n, because there are n ways to pick 1 element from a set. And similarly, there are n ways to pick n minus 1 elements. And and choose n is always going to be 1. So this is already somewhat amazing, at least to me at the age I was. Why should this be an integer? It would mean that this number n factorial would have to be divisible by k factorial, and it would have to be divisible by n minus k factorial as well. And while that might work for some small examples, why that should work for every example was really remarkable. So the next thing I learned about binomial coefficients was Pascal's triangle. So Pascal's triangle is very interesting. You start with a 1 at the top and 2 1s here. And then you say, well, I'm going to add this one to 0. Well, that's 1. And these two together, well, that's 2. And this one to 0, well, that's 1. And then 1 and 2 together is 3. 2 and 1 together is 3. 1. And 1, 4, 6, 4, 1, 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, 1, 7, 21, 35, 35, 21, 7, 1, 1, 8, 18, 56, 70, 56, 18, 8, 1. And let me go up to 9 anyway. 1, 9, 26, 74, 126. Make this more visible. 126, 126. 74, 26, 9, and 1. And here we get this by 4 plus 6 is 10. 10 plus 10 is 20. 20 plus 15 is 35. So below every number, we'll write the sum of the two neighboring numbers above. And these are the binomial coefficients for n equals 1, or n equals 0 rather, n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, and so forth. In particular, we have that n choose k is equal to n minus 1 choose k plus n minus 1 plus choose k minus 1. And you can think about this in a very interesting way. If this is the number of subsets of a set with k elements, then pick an element. Pick an element and call it special. Then there are n minus 1 elements left. This is how many subsets of n, of a set with n elements, subsets of size k, which don't pick our special element. And this is the number of subsets of size k, which pick our special element. So whole books have been written about Pascal's triangle. Whole books, just talking about the beauty and the patterns which are in Pascal's triangle. I'm not going to try to duplicate that, but when I was an elementary school student, this was a really amazing thing for me because somehow these patterns were all coming out of this equation down here. And we're all coming out of the fact that n choose k counted how many subsets there were of size k. Well, when I went to high school, I ran into binomial coefficients a different way. So let's start off by just asking x minus r, 1. So this is a linear function, a linear polynomial that has one root, x1. The one place where if I plug in, or if I plugged in r1 for x, I get 0. So we call such an element a root. And this is a polynomial, a linear polynomial, which has r1 as a root. Okay. Well, quadratic polynomials have the two roots, r1 and r2. This is a polynomial. If I plug in r1 for x, I get 0 minus r1 minus r2, so that's 0. If I plug in r2 for x, I get 0, or r2 minus r1 and 0. So I get 0 if I plug in r1 or r2. And if I multiply this out, what do I get? I get that expression. Just like if I multiply this out, I get that expression. Well, maybe that's not much of a pattern, but let's try it for 3. X minus r1, x minus r2, x minus r3. Well, this is x cubed minus r1 plus r2 plus r3 x squared plus r1 r2 plus r1 r3 plus r2 r3 times x minus r1 r2 r3. And if I plug in, if I do this for 4, I get x minus r1 times x minus R2 times x minus R3, and that's equal to x to the fourth minus
You missed the one
R1.
factor x
Oh,
minus
sorry.
R4.
X minus R to the fourth here, R sub 4.
Yeah.
Well, I get x minus x to the fourth minus R1 plus R2 plus R3 plus R4 x cubed minus R1 R2 plus R1 R3 plus R1 R4 plus R2 R3 plus R2 R4 plus R3 R4 x squared. That's a plus that. And then I get a minus R1, R2, R3 plus R1, R2, R4 plus R1, R3, R4 plus R2, R3, R4 times x plus R1, R2, R3, R4. Now, if you really wanted to, we could do it for 5, 6, 7, and 8, but the pages of the paper would just be filled with things. But let's look at something. We always have highest power of x is how many roots we have. The coefficient of the next highest power of x is the sum of the roots. The coefficient of the next highest power of x is the sum of the products of the roots taken two at a time. The next highest power of x is the sum of the product of the roots taken three at a time. And the next lowest power of x is going to be the sum of the roots taken four at a time. So I want to define a function. Let's call it E1. And I'm going to define it on an infinite number of variables. So E1 is just going to be the sum of things taken one at a time. And E2, again, I'm going to make this a sum on an infinite number of variables. It's just going to be the sum of things taken two at a time. Anyone want to guess what we want E3 to be? Let's try
can
this.
unmute your microphone and talk. Erica is saying 3 at a time.
3 at a time is correct, Erica. We're going to take them 3 at a time. So E3 will set to be, again, infinite number of variables. And now I'm going to write down a formula. So if a polynomial has roots R1 to Rn, then x minus R1 product to x minus Rn is just x to the n minus E1 of R1 to Rn, and I'm just going to fill in zeros for the rest, times x to the n minus 1 plus E2 R1 to Rn, and zeros for the rest, x to the n minus 2 plus E n minus 1 R1 to Rn, and zeros for the rest, x plus E1 plus En of R1 to Rn, and zeros for the rest. Okay, so this is nice. In mathematics, we want to give things names so that we can remember what they are. We call the EI the elementary symmetric functions. So the E1 through N are the n elementary symmetric functions. And we saw that we could write down exactly what they were. Okay. So let me ask the question. What is EK of 1, and then all the rest being zeros, where this is n ones? Okay, well, let's think about this. EK on this set would be, we take all of the we take all of these n spots here, we take them k at a time. So for every subset of n of size k, we get a 1. So this is the sum of 1 for every, counting over all the subsets of size k. So ek of 1 repeated n times, and then zeros on forever, is just n choose k. So x minus 1 to the n is just the sum, and this is a fancy way of writing, add all the things on the right-hand side together as we increment these from 0 to n of minus 1 to the k, n choose k, x to the k. Now, if you want to, actually, I should probably write n minus k. Yeah. And I could also write it as n minus x plus 1 to the n and this might not seem a lot, but here we have the most brilliant idea to date. In the history of counting. Clearly the most, in my mind, clearly the most brilliant idea to date in the history of counting that's ever occurred. Let's take x plus 1 and raise it to the m plus m power. That is x plus 1 to the m times x plus 1 to the n. So that means the left-hand side is the sum n choose k, x to the n minus k, k equals 0 to infinity. And the right-hand side is the product, j equals 0 to n of m choose j, x to the, this should be m plus n minus k, m minus j times the sum L equals 0 to n, this is an n. No, if this is an m, and that's an m, this is an n, and this is n, choose L, x to the n minus L. And so if I look at this, I get that n choose k is the sum z equals 0. So this should be n plus m. Z equals 0 to n of m choose z times n choose z has to be k. So k minus z. And this is the sum k. If you look at this boggled my mind that let me repeat it. Z equals 0 to k of m choose k, n choose k. So that 3 plus 4 choose k. 3 plus 4 choose 2, for example, was k minus z. This was 3 choose 0 times 4 choose 2 plus 3 choose 1 times 4 choose 1 plus 3 choose 2 times 4 choose 0. Now, if you think about it another way, you could say you want to choose 7 elements. You have 2 subsets. You can choose 0 from the first subset and 2 from the second. You can choose 1 from the first and 1 from the second. And you can choose 2 from the first and 0 from the second. But this idea that we could use the fact that our function counted the coefficients of a polynomial is really the most brilliant idea in the history of counting. Okay. In college, where did I see binomial coefficients? Well, they became pretty sparse. actually, in my college career. But I did see them really twice. One was this time. Introduce what's called the Q binomial coefficient. Now, what does this Q binomial coefficient look like? Well, looks like 1 minus Q to the N, 1 minus Q to the N minus 1, all the way down to 1 minus Q to the N minus K plus 1 over 1 minus Q squared, all the way up to 1 minus Q to the K. So this sort of looks like n factorial up on the top, and it sort of looks like k factorial down at the bottom. But instead of being an integer, this number, n choose k, choose q, is a polynomial, integer polynomial in Q. A little strange. Again, you have things like Q, 0 choose 0 is 1, which is Q, which is the same as 1 choose 1 is Q. But 2 choose 1 Q is 1 plus Q. 3 choose 1 Q is 1 plus Q squared. And in fact, n choose 1 Q is 1 plus Q squared plus Q to the n minus 1. Well, the point is, and the reason to talk about this is that even though these are very different than the binomial coefficients, they still have a similar rule. N minus 1 choose K. So Q plus Q to the N minus K. N minus 1, K minus 1, Q. So it would look like binomial coefficients, except that this Q is behaving well. If you set Q equals 1, and let me say that correctly. Because if you just try plugging in q minus 1 equals 1 in the formula, you don't get this. But if you do it correctly, you see that n, the binomial coefficient at 1 is just n choose k. So that in some sense, the binomial coefficients are just a little generalization of the binomial coefficients. And we even have a polynomial. We look at 1 and we have q to the k x, and we product all of these from k equals 0 to n minus 1, then this is a sum of n choose k sub q x to the k, but I have to put a little weight here in front to make that work. So I don't suspect that you've seen binomial coefficients a lot, but they are a surprising thing that occurs a lot in modern physics. And the ideas behind them are closely related to modern physics. So I told you about my life in high school and elementary school and college, talking a lot about binomial coefficients, but I want to go even a little further and talk about my life in graduate school. So you might think that you've been going to school forever, but I started going to school in 1960 and haven't stopped. So that's been a few years. And when I went to graduate school, I found a new fact about binomial coefficients. Okay. And I'll just give you the case n equals 2 here. And if you look at this question, x times y times 2. Choose 2. Well, that's a expression. That's a natural expression. You can ask, well, is this the simplest way to write this expression? And I'm going to give you what in my mind is a mind-blowing identity. This is x choose 1 squared times y choose 2 minus 2 x choose 2 y choose 2 plus y choose 1 squared times y choose 2. Or sorry, x choose 2. Or if you prefer numbers, this just says that something like 3 times 4 choose 2 is 3 squared times 4 choose 2 minus 2 times 3 choose 2 times 4 choose 2 plus 4 squared times 3 choose 2. And if any of you told me that you knew this before you started this talk, I would say I would be really impressed, because it's unclear as to why this should be. And what happens is you can show this using properties of coefficients. But this was not what really blew my mind when I went to graduate school. What really blew my mind when I went to graduate school is that X choose Y choose K is that there's a polynomial that depends only on K, so that this is a polynomial in X choose 1 to X choose K, and Y choose 1 to Y choose K. So this is not a fact about 3 and 4 or about X, Y choose 2. There's a polynomial for every K that works, that allows me to write X times Y choose K as a product of coefficients of polynomial in the binomial coefficients X choose 1 to X choose K, and Y choose 1 to Y choose K. And not only this, what if we take N choose K and we choose L? There is a polynomial in K and L, which lets me write this in terms of N choose 1 to N choose KL. So, just to give you an example, N choose 2. Choose 2 is always N choose 1 times N choose 3 minus N choose 4. So for every value that you plug in on the left-hand side, okay, every integer value you plug in on the left-hand side, you're going to get the same value on the right-hand side. It means that this polynomial that you have on the left here, N times N minus 1 divided by 2 times N minus 1 divided by 2 minus 1 divided by 2 is equal to N times N choose 3 minus N choose 4. Now, people often write doctoral dissertations on a lot of bizarre things. And it would be unfair of me to say that this was my doctoral dissertation. But the ideas behind it were central to my doctoral dissertation. So I've taken you now from elementary school to a doctoral degree, just looking at binomial coefficients. But what does a mathematician do with their life? Well, in the postgraduate world, I was called to look at something very strange. So to understand this very strange thing, let's go back to this Pascal triangle. And let me take some entries here. So let's take these three entries. 126, 70, and 35. So this is 7, choose 0, 1, 2, 3, 4. This is 7, choose 4. 8, choose 4. And 9, choose 4. Okay. And now let's take these three entries there. That's 6, 4, choose 4. 5, choose 4. And 6, choose 4. Or if you want me to write it another way, I could write it as 4, choose 0. 5, choose 1. 6, choose 2. 7, choose 3. 8, choose 4. And 9, choose 5. These two are equal because 7, choose 3 is 7, choose 4. 8, choose 4 is 8, choose 4. 9, 5, choose 5 is the same as 9, choose 4. This is an integer. The reason I found this was because I was trying to count something. And this is what I was counting. And so I showed that n plus k choose k times n plus k plus 1, choose k plus 1, n plus k plus l, choose k plus l, divided by n plus 0, choose 0, n plus 1, choose 1, n plus l, choose l, is always an integer. Now, if you notice, this is a binomial coefficient of binomial coefficients. And I obtained this not by sitting down and saying, what sort of binomial coefficient of binomial coefficients could be. I was counting something, and I was counting and doing some algebra and rearranging, and this happened to fall out. I later found out that this was known in 1861. But I didn't know it when I did it. Okay. So you can ask the question, what about replacing the binomial coefficients with q-nomial ones, q-binomial coefficient? Is it an integer polynomial? And the answer is yes. And today you can know that something, or sorry, 2021, you can know something that was new in the mathematical world last year. Because up until last year, it was unknown that this was always an integer polynomial. The answer is yes. What we don't know is, what does it count? So I've used your indulgence quite a bit this afternoon to talk about my life and things which occurred in my life from a mathematics point of view. I do have a life outside of mathematics, but my mathematics life is very rich and very enjoyable. I don't expect that all of this will make a lot of sense to you right now. But what you should know is things that you think are just things that you learn and pick up every day that you see, like binomial coefficients, are things that can stay with you always. And the kinds of questions that you can ask about them are limitless. And there's always a future to push back the limits of knowledge. My days to do that will soon come to an end. But there's real hope for you. So I want to encourage you all to study mathematics. And with that, I think I better turn things over to Michelle before she complains that I have gone way, way, way too long. So Michelle.